Yeah, hello everybody. Welcome to our webinar, Long-Term Stable Methods Thanks to Drift Correction. My name is Rainer Schramm, and I would like to present today strategy of drift correction and guide you through this issue. We have to talk about how X-ray fluorescence is working, the techniques which are used. We go also to important points like what is an MCA calibration, what is peak positioning, what is drift as the main issue, and how can we correct for any drift, what kind of drift samples we could use, and I want to summarize my presentation. So let's talk about X-ray fluorescence. We have to understand the principle. Normally what we do is that an X-ray tube is creating X-rays. They are going to our sample, and in our sample, the X-ray will take out electrons from the inner shells of our atoms. So that means the atoms are ionized, and the gap which is formed is then filled up by electrons which fall down from higher shells. And the difference in energy, this is then sent out as X-ray fluorescence. And what we normally see then in our software is a kind of spectrum, a spectrum in a way that you have lines which are then formed like a peak. And in this example, we have an iron K alpha and iron K beta line. And you see here how this will be presented. And this is what we then call count rate or intensity, and we take for calibration. And so that means when we see a drift, that would mean that this signal changes over time. And we would like to use the drift correction, to keep control of this change. And this is what we will talk about. So what changes over time? It is actually the location of the peak. So it could go to the left and the right. And of course, the intensity, that means the total surface or the height of the peak will also change. So we have first to look on energy dispersive XRF and all the components we use in the hardware. And like you see here, this is a simple arrangement of direct excitation. That means the tube excites the sample from underneath, and the detector is watching the X-rays coming from the sample. And then there could be also kind of a filter changer in between tube and sample. There's another way also to do energy dispersive XRF, and this is by using polarized excitation, and then a target is additionally placed between tube and sample, and in this way we have one hardware component more. And normally these instruments come like a tabletop device, benchtop device, or a so-called handheld instruments. They are all based on energy dispersive technique. And the parts which might now influence our drift are, of course, the peak positioning with the so-called MCA controller. I will explain a little bit later. Then, of course, we have our X-ray tube where we have the voltage and the current. We have the filter in between tube and sample or the target. Then we have the detector. We have, of course, the atmosphere we are measuring under. Also, this will influence our intensity, and all these together will make a signal change over time. If we look the same on the wavelength dispersive XRF, on the excitation side, it looks quite the same. We have our tube, which excites the sample from underneath. We have kind of filters in between. And then on the other side, the detection now is a so-called goniometer. That means the goniometer is selecting one wavelength to guide to the detector. So that means in our measurement here, in the detection, only one single wavelength is detected. And the way this is done is that we use a crystal which is reflecting the signal from the sample under a certain angle. And by changing the angle, we change the wavelength which is selected. And so in the end, these instruments also come nowadays as benchtop systems or as floor standing systems. And the parameters we have to look at is again the peak positioning, then of course our X-ray tube with voltage and current. The filter might change our signal, the collimator from the goniometer, the crystal, the detector. Then we have something new in wavelengths dispersive. This is the PhD window setting. And again, the atmosphere we are measuring under. That means all these parameters have an influence to our signal. And by aging and changing over time or exchange, this has a direct influence to the signal we use then for measuring our samples. So let's do first energy dispersive and talk about MCA. MCA is the multiple channel analyzer. And when we look on our spectrum, we will have here continuous background and we will have our peaks on top. And this multi-channel analyzer is taking this into channels. And what we want or what we need finally is energy. That means we need a transfer from channel to energy. That means this peak positioning in a certain channel has to correspond to a certain energy. And that means, therefore, we need a calibration which tells us which channel belongs to which energy. And this is why you have to do on a regular base an MCA calibration. And it's just the peak positioning which is calibrated with that. Don't mix this with intensity changes over time. This is a different story. Perhaps the same sample could be used. This depends on your software arrangement, but generally the MCA is only peak positioning. In wavelengths dispersive, we have the same thing, but there it's the line positioning. That means when we build an application, we have to define at what angle we measure our sample together with a certain crystal and a certain detector and collimator. And when we use these settings, we make a scan and we will get a picture like this here. And then we will define the final position of our measurement by setting the angle to the maximum peak intensity. And this is important because this guarantees us that when there is a little bit of movement to the left and the right, we have still a very stable signal, while when it would be here in the slope, it would make a big difference. And in this way, by selecting the maximum line positioning, we get a long-term stable method. Additionally, normally you set your background positions in a range which is just a bit off from the line and free of any line overlaps. The other thing you have also to take into account is the PhD setting of the detector. This is also only for wavelengths dispersive. And perhaps a small explanation what this means. Normally, you are measuring here with the setting you have selected just one single line, so one wavelength. The detector itself, what the detector is measuring is still an energy range. So we still have to tell the detector what kind of signal he has to collect to create finally the intensity of a certain element. And this is quite straightforward. Normally, you set it just from the left side to the right side to just collect all the signal. And you just have to make sure that your window is wide enough so that all the radiation is collected. But there is for three elements. This is titanium, vanadium, and chromium. Is a special case in combination with a flow counter that there you also have this escape peak. And then you have to make sure that your lower limit is either on the left side or in the middle of this escape peak, because very often the standard setting of the software is just on top of the peak, and this is also not good for our long-term stability, because we want that when this picture is moving a little bit from the left to the right, that still everything is collected inside the limits. And this is why you have to make sure that the setting of this lower limit and upper limit is really set in a way that still the whole picture is collected. Okay, but what means drift correction? What is changing over time? It means that the intensity could be higher of our line or lower, and the background could also change. And of course, both could change in a different way. That here you get a kind of a slope, and here it's just the intensity which changes. And the reason for this is then, for example, the peak positioning, what I told you already, so that you don't do your MCA and your line positioning correctly. Then your system is very sensitive to any movements. Um, then the X-ray voltage, X-ray tube voltage and current. So they could give a different intensity over time. So it's a kind of aging. Also the same for the filter, the collimator, the crystal, the detector. They all could change a little bit over time and then be the reason for the changement in the peak formation. Also, this PhD window should be set correctly. And of course, the atmosphere also plays a role. Elements which are sensitive to vacuum, like the very light elements. Of course, if your vacuum is getting worse, then the intensity is going down. So also this has to be taken into account. The strategy now to correct for a drift is in the easiest case just a high sample. That means we use a drift correction sample which has an intensity which is in the upper range of our calibration, so that by measuring it at the time of the calibration, and then a bit later, when, let me say, 1 day, 1 week, 1 year later, you could detect directly the change in sensitivity. And by establishing then a factor, you can then correct all your measurements to go back to day 0. But when you just use only a high sample, this means that 0 concentration must be 0 intensity. And this is only the case when you use net lines. That means before you measure, before you correct for drift, you have already subtracted your background. And this is in energy dispersive mostly the case, because there the background is always subtracted and all the calculations are done on net intensities. So a high sample is good enough. But in wavelengths dispersive, you could also use cross lines. And then, of course, we need a different strategy. And this is shown here. So when the background changes differently than the lines, and you do not do any background subtraction in your measurements, then you need a high sample still to correct for your sensitivity, and you need a low sample for the background additionally. Yeah. So then we use a high and a low drift correction sample. It will be based on cross line. And this could be the case for sequential WD XRF, and especially also for simultaneous instrument. A simultaneous instrument is when when you have more than one detector arranged around your sample, and they all measure your elements simultaneously, but then these detectors are only adjusted for one single wavelength, and they cannot measure any backgrounds. So that means they are always measuring gross lines without subtracting the background, and then a low drift correction sample is obligatory. But we also have to think about a measurement error, because when your drift correction measurement has a high error, you would introduce an additional error to your system, and this is what you don't want. When you want to correct for the drift, you want to go back to the calibration on day 0 so that all these aging effects are taken away. And then the drift correction measurement must be as precise as possible. For this, we have to talk about how you detect your measurement error. And this is the case that you take your complete intensity you collect in the measurement time, and you just take the square root out of it. Yeah? This ratio or this ratio relationship between the error and the intensity, this is shown here, that you just increase your count rate, or your counts, sorry, not the count rate, it's the counts in the measurement time. And then you see how the error also increases, but relatively, of course, the error is getting lower. So here an example. For example, we have a count rate, and this is per second from 1,000, and we measure 1,000 seconds. We have a complete intensity of 1 million counts. This is what we collected in these 1,000 seconds. When we then calculate our error, you will see that we have 0.1% relative error. And this is just close to the theoretical error of an XRF, what you could achieve the best. Normally, I would say an XRF cannot be better than 0.05%. Yeah, this is more or less the theoretical best mark, and that means when you measure a drift sample with 1 million counts, you will be exactly on the lowest error possible, and you will not introduce an additional error in the system. And of course, this is important for major components. If you go to minus and trace elements, you will never be able to collect such a high number of counts. Then, of course, also less measurement time is possible. So you really have to look into your application, what you really need, and in this way then select your measuring time. And typically, I would say you should be in the range of 100,000 to 1 million counts for your drift samples, so that your error is in this range, and then it can be negligible finally as a contribution to your precision and accuracy. Now, what kind of samples do we use to make a drift correction? Over all the years, we made the experience that silicate glasses are the most stable samples for this, because if you use metals, they could corrode, they could create an oxide layer on top, which will change the signal over time. And if you use any pressed pellets, they could also take humidity and change the surface structure, and the same is for fuse beads. So silicate glasses are considered as the most stable samples, and they are very stable over time. They are also stable under X-ray conditions and very high radiation conditions. They can be made with high intensities. Of course, you should have the same elements as in your application, and you could clean them, for example, with alcohol, and in this way make sure that all fingerprints and dust what has formed can be taken away. As an example here, a drift monitor set for cement and raw materials. These are the classical 14 elements between sodium and zinc, plus chlorine and fluorine. And so you see the three silicate classes are designed in a way that for every element you have a high sample, and the other two you could then use one or the other as a low sample. And in this way, you see the blue figures is then always the high sample, and they are very good for sequential WD XRF. You could combine them also for simultaneous instruments to have a low and a high sample, and also good for fuse bead application with background, and also for press pellet applications. So this is, for these kind of elements, quite a good selection. But of course, there are other applications like metals, like ferroalloys, like slags, and so on, where very often you have other elements out of the 14. And for this, we have created a new set of drift correction samples. It's a set of 6 samples, which covers just all the elements shown here. And you see here in the colors also the range of concentrations which are represented from these samples. You see the green ones are in between 10 and 100% concentration. Then the blue ones are in the 1 to 10%, and the yellow ones are then in the lower range because these elements mostly just come up in minor concentration. If there's an element missing, like here some rare earths, you could just go to the neighbor element to correct for this. So this is then the way to compensate any gaps in the system. And so we have designed 6 samples. We call them drift correction, DC samples. And there's one special case that the DC1 you can get with and without uranium and thorium. Then it's called DC7. So with the 6, then you could just have a selection of all the elements, even also uranium and thorium. These are silicate glasses. That means they all contain silicon oxide in high concentration. In case you need a low silica drift correction sample, we have another extension. That means these are here phosphate glasses, which come without silicon oxide. And then we have here just added a little bit of silicon oxide to allow also a low silica drift correction sample. And here you will see how this distributes over the periodic table. So you see here in red the high and in blue the low sample. So you see for every element you find always a combination between a high and a low drift correction sample, so that in complete you will cover the whole periodic table then to get all the elements drift corrected. Important is always that you use your application settings to measure them, that you have then exactly the same conditions. They are also designed in a way that if you look only on one sample, there are as less line overlaps as possible between neighbor elements, so that you always have freestanding peaks to get the best precision possible without any line overlaps. Yeah, and then the examples how this is really performed in your software. There are 2 different ways to do this. One way is that you directly define in your application, you link your corresponding line with the drift sample. Like here in this example, it was linked to a bottom SOS and a top SOS. That means a low drift sample and a high drift sample. And you see here, this was the intensity measured for the low and the high. And then the system calculates with the 2 values the drift correction for this line in this application. This is one possibility. The other possibility is that your lines are coming from a line library, and in the library you link your lines to the drift correction samples. You could also link 1 or 2, or sometimes even more. And but I think 2 is really the maximum you should use. And then every application which is using that line is then automatically drift corrected over the time. Yeah. So this is a different strategy. This is a bit more optimal for the time. That means you have to measure just once your global drift correction, then all applications are done. Here you have perhaps to measure for every application your own drift correction samples. So this could be more time consuming. So then an example from our X-ray system in the laboratory, I have collected a drift over 5 years, and you see an interesting picture that the very light elements like sodium and fluorine, they show in 5 years something like 20% drift. Then the elements which are vacuum sensitive, they show in the range of 10 to 15%, and all the others, the heavy elements, are in the range of 5%. And of course, this is the same for K lines and lines, exactly the same picture. If we go into detail, for example, here, iron as a heavy element, you see the very small change over 2 years now. And if you look on phosphorus as a light element, you see really a significant drift over 2 years. And this is just what you see, and this is what I have collected in the 5 years picture, so that you get a feeling on how does a system change over time. This is not critical, this is normal, and with the drift correction, you continuously have to monitor and to perform. You can get this under control. But how? How do you do that? So my recommendation is that you measure control samples, and in the moment the control samples go out of specs, you then perform your drift correction, and then if it really was a drift, your control sample will get back on the line, and in this way you can keep all your calibrations to the right way. But of course, you have to do a regular check. And you have to define your stability criteria that you know when are you off. And if you're off, then you have to perform your drift correction. And this means you have to get this all installed properly so that for every setting of your line measurement in an application, you need a corresponding measurement in the drift measuring program. So to summarize, is first, in the beginning, you have to establish stable conditions. That means when you select your measurement conditions, you have to make sure that, for example, the line position settings, the PhD settings, the MCA calibration, that they are all under control so that any kind of movements there have nearly no influence to drift. So then you minimize the drift already from the beginning. Then, of course, you have to select your drift samples according to the applications and the measurement conditions you are using. This has to be installed in your spectrometer software, and it has to be installed in the same time you perform your calibrations so that you really freeze your calibration settings in the drift measurement. Then you have to monitor, and when your check samples are out of specs, then you do your drift correction. And then finally, when you do this all right, you will see that you can use your calibrations really for a long time. Okay, that was my quick run through drift correction, and I hope I could point to all the important steps you have to be careful and you have to get under control so that you have really no issue from the drift, and you don't have to redo your calibration in a very short time period, so that you really can trust to your calibration over a long time. So now I'm curious for your questions. There is one question. Those drift samples can be used for method development, for trace element and rare earth element quantification. Yes, you have seen from the table that we cover nearly all elements. And if there is one missing, you can always use the trick that you just measure an element group under the same measurement conditions. And then, of course, you can use also a neighbor element, which is available in the drift correction sample to do also drift correction for elements which are not present. There is another, what about Uniquant? Uniquant comes with an own drift correction set. And this is important that you use this because there the lines are preset. So you really have to trust into the Uniquant recalibration standards. Otherwise, your drift correction will not work. I mean, you could use our standards as well, but it would need then, of course, a bit of modification, for example, of the measurement times. More questions? Line library, how does it work? Of course, this is a bit different from manufacturer to manufacturer. But normally I would perform this in the following way, that you set up, you have your application. The application has, of course, the line selection, and the application normally allows you to establish on these settings a drift correction measuring setting, which sometimes is just the same settings and the measurement times are just, for example, doubled or are measured 4 times. This you have to check according the rules I have given you if this measurement time is right. And then this extra measuring set for the drift correction, this is then used to correct for the drift correction. This is one possibility. The other possibility is that you really can set up manually a drift correction measuring program, and you have then to add the lines from the line library to establish then really the measurement settings. Next question. How can I perform this drift correction with the same approach? Yeah, perform means then you measure, you start then the drift correction measuring program. And then, for example, you have set up 6 samples. You have to put them on the autosampler and then to perform it. And then always you get a report, and the report is telling you how much drift was really detected and how much drift correction was performed. If I make drift correction as usual, is it okay for Uniquant? Okay, Uniquant has an own drift correction program, and this you should just perform on a regular basis. Also there you get a report, and then you see how has performed. There's another question, can this be used for portable XRF? Portable XRF, I made the experience that they are very stable. So there's probably no drift correction really necessary. But this you can check with your manufacturer, because, for example, on our portable XRF, we have a control sample. We measure on a regular base. And as long this is always good, you don't need to do any drift correction. So let me see, any more questions here? Not for the moment. You know that you can always send me an email if there's any open question and you would like to discuss perhaps also some software issues, how you can really perform this. And also what happens sometimes is when you break a drift correction glass, that it falls down, it drops down, then it's a special procedure how you will introduce a new version into your software. And there also we can help you. Okay, then I would say thank you for listening to this webinar. And I would be very happy if you listen to our next webinar. And yeah, I wish you all the best for the rest of the week. And thank you very much for listening.